After displacement, the next obvious thing to talk about is velocity and acceleration. If we can define velocity, of course, by the way that the position of a particle changes with time. So if it was originally at position A and then some time t later, it was at position B, undergoing a displacement delta r, then we would say that the velocity, the average velocity during that time interval, is equal to delta r over delta t. The instantaneous velocity, of course, is the limit that the delta t goes to 0. So we would have v as a function of t is equal to dr dt, where dr is just an infinitesimal displacement. So to get this value, we really should go back and look at what r is. Of course, r is the sum over I, 1 to 3, of r sub I, ei, unit vector. But of course, we want the time dependence, so I'm going to write this explicitly out here. The time dependence of each component multiplied by the unit vector, which may also be time dependent. dr dt will then be simply the time derivative of this sum. Now, because the components themselves can be have time dependence as well as the unit vectors, then we'll get two terms. We'll get dri dt times ei vector plus ri dei dt. Now this term right here looks a little funny, especially if we talk about what that means. That's, say, for example, dx hat dt. How does the x component or the x unit vector change with time? Right? If x hat here points this way, later on when we're up here, x hat still points in this direction, and therefore dx hat dt is 0. And same with dy dt and dz dt. Which means that effectively, when we're using Cartesian coordinates, this term goes away. So in Cartesian coords, v is just going to be equal to the sum over I, dri dt ei. In other coordinate systems, that's not the case. We'll get to this a little later, or soon, but just as a preview, if I'm looking at, say, polar coordinates, just two-dimensional polar coordinates, and I go from position A, okay, to position B, and I want to talk about polar coordinates, what's happening here is my rho hat, the radial vector, unit vector, rho hat points like this, and then later it's pointing in a slightly different direction. Now that different direction is going to depend on the time. Just again as a preview, rho hat is going to be equal to cosine of the azimuthal angle being this angle, times x hat, plus sine of the azimuthal angle times y hat. And if the azimuthal angle itself is changing with time, as this thing, say, spins around, say goes as omega t, then you'll see that d rho hat dt is not equal to 0. I'll get a derivative here, and a derivative with respect to time here, and those won't be 0. So in general, dEi dt is not equal to 0, and we'll have to be very careful when using non-Cartesian coordinates. Of course, v itself is a function of time, so we can also write the acceleration, which is going to be, in general, a function of time as well, dv dt. What this, again, just to be quick, looks like is something like I started off with this velocity here, whatever speed we had, and direction, and then later there was a different speed and direction, and this is going to be delta v, and we'll just let that delta v go to an infinitesimal change in velocity. Well, that's just going to be, in Cartesian coordinates, of course, that's just going to be a is equal to dvx dt x hat plus dvy dt y hat plus dvz dt z hat, or using our summation form like that. In general, we also have another term that was vi di ei hat dt. We'd have both of these terms, but in Cartesian coordinates that goes away. Only in Cartesian coordinates. Last thing about nomenclature here is that, like many people, Taylor uses a dot notation for differentiating with respect to time. For example, v is x dot, comma y dot, comma z dot, and a would be vx dot, vy dot, vz dot. Here this dot just means differentiate with respect to time. You'll see that over and over again in this class.